So welcome to the robotic lecture. So anyone you didn't can last week? Okay, so 3, 4. Because we have grouping for case study and projects. So we'll be grouping them. So this is our schedule for this semester, which has been mentioned in the last week. So now we're here. So today we'll have a lecture for the sensor and actuator. And here will be the case study presentations. So if you already have your group, then so you can check with your date and also we will have a proposal for the final report, and this is the midterm exam. And also we will have progress discussion and final presentation. All these three will be for final projects. And we have a Facebook group, so if you haven't joined, please join it. We will upload lecture notes or other information to our Facebook group. So these are the group that have been assigned for case study. So if you haven't been assigned, please come up here so you can choose your topic. Just come up here. Special robotics, special voice. Robotics, pipeline construction robots, and operation method, and market research. So for the special robotics, we will have one member left, and these 4 are 4 new topics. So we have an update because a student has joined our lecture. So this one will still have one member to join. So this is the spatial robotics. It's not the robots defined in other fields. So maybe something like using the cable to do a movement or something very special. So we this category. So if the robot is not falling to this category, it will be falling inside the spatial robotics. So it's quite a wide range topic. And this is a walking leg robotics. So like humanoid, the dogs, and maybe something like spider or other animals will fall inside this walking leg robotics. And for the pipeline inspection robots, it do the inspection inside the pipe. So this is kind of robot. And this is the calibration method. So if you are interested, you can choose this one. And also we have the market research for industrial robots. And this is the CNC machines. So yes.
And would you take the training the CNC machines? Would it be possible for us to take robotic CNC machines?
Pardon?
Sorry. And the last topic we presented, the 5 axis. We too will take the topic.
Oh, you okay.
That's okay.
Okay. Yeah. So you can come up to here after the lecture. So we also have final projects. So I think just how you have around four people. So who hasn't been assigned the final project group? So this, you have already. Okay, so 4. Then I think maybe we can have 4 of this group have 6 people. Yeah, because it's maybe quite hard for you. Or you want to join as 4 as a group? Then up to you. Yeah.
Rosa, I can ask people in the same group and I join this group.
You mean you want to join?
Yeah. Well, I only want I need to find the team to join.
Yeah, because now you have 4 people who haven't been assigned to a group. So maybe if you want to choose to do the project as 4 people, or you want to just distribute it.
Maybe.
Okay.
I can join this.
I want to join the group.
Okay, so maybe later during the break we can come to the teacher assistance. So all group will have 6 people, and others will have only 5. So we'll be doing the sensor actually today. So what is a sensor? A sensor is a device that measures a physical quantity and converts into signal, which can be read by an observer or by an instrument. So it's like a sensor, maybe you can like measure the distance, or you can measure like other things, but you will convert into like something like electrical value, then you can read it. So usually sensors convert physical variables to signal variables, and we have passive sensor, and we also have active sensors. So the passive sensors, you do not need to add external energy, and you can when we're doing a measurement. But the active sensor, we need like electricity or something like that, the voltage to do the measurements. And these are the 6 signal energy domains. So the first one will be the radiant. It's covering the full spectrum of the electromagnetic radiations. And the second one will be the mechanical. It's something like distance, velocity, size, and force. And the third one will be thermal is something like a temperature or doing heat. And the fourth one will be the electrical. So it's covered electrical parameters such as current, voltage, resistance, and capacitance. And the fifth one will be the magnetic. So it covers magnetic field parameters such as strength, flux, etc. And the last one will be chemical. And we also can divide it into three axes. So this one will be the input energy and the output energy and motivating energy. So we can base all the sensors inside depends on what input energy it takes and what is the output energy. And we have some sensor rating parameters. So first one will be the sensitivities. So sensitivities is the relation between the output and the input. So the output change, if the output change, like for example, is like the voltage output is 0.1 voltage for every centimeter distance measured. So the sensitivity is 0.1 V over cm. And also the cross sensitivities, because we have our direction of sensitivity. So the cross sensitivities is the other directions. So it is orthogonal to what we want to measure. And the range will be the lower and the upper limits. So it's like a sensor which can measure between 10 to 80 centimeters. So the range is 70 centimeters. And also we have the resolutions. So the minimum difference between two measures. So for digital sensors, it is usually the analog to digital resolution. So it's 0.02 voltage. So it is the minimum difference that you can measure. And also we have the linearity. So this is measure how linear the relationship between the sensor's output and the input signals. And we will have a graph. So this is a graph for a sensor. So here will be the input range and the output range. So we can see here. So usually we will have the if we start from the 0, but we have an offset. So this will be the offset. And also this one will be a resolution. So because usually in our real life, this will be a continuous, but due to the digital problem, so we have a resolution. So this is the minimum distance we can measure. And also we have the linearity errors, because if we assume like ideally the input and output should be a straight line, but in reality we measure is a curve. So this is the linearity error. And these are some non-ideal measures like asymmetry. And also this is the bias, we have the offsets. And some sensor we have a dead zone, that because like if here is we can measure, but in between we cannot measure any values because it is a dead zone. So non-linearity, and also the scaling factors, it is have the scaling factors, and also the normalization. So this is the resolutions. So what can we do with it? So all the sensor we need to do the calibrations. So the calibration is the relationship between the physical measurements, variables input, and the signal variables for the specific sensor. And accuracy, the accuracy is the instrument defined as the difference between the true value. So actually, so in a simple, very simple definition, it is just the true value is here. You want to do how close is your your value close to the true value. So that is the accuracy. and we have the repeatability in robotics, or you can call it precision. So this is if you doing the same motion every one time and another time, and will you get the same value? So this is the repeatability. So we can see it here. So these are the measurements, and this is the average value of the measurements, and this is the target value. So you see this is the low accuracy with low repeatabilities. So if we change to a better component, maybe we can increase our repeatabilities. So like we can have all inside here, but we don't have we have low accuracy because sit here it will be a true value, and with calibrations we can shift our measurement to the true value. So this is the definition in robotics. So accuracy is how close a robot can come to and give given points in its workspace. So usually it depends on the machine accuracy. So we can have it's due to like assembly or flexibility effects of the links or something payload change. So or the error control. So here we can improve by doing the calibrations. So repeatability is how close the robot can return to a previous taught point. So usually if we want to teach a robot to do a path, to do a path planning, then if the repeatability is very low, then the robots you cannot do the path. So it depends only on the robot controller and measurement resolutions. So we have two errors. So this one will be a systematic errors, and another one will be a written errors. So if you look at a systematic is due to because something like if you do some assembly or something, because so all the errors will be shifted into same value. So this is deterministic. So it's caused by factors that can be model. So this one will be a shift. So this is systematic errors, also called a bias. And the random errors is non-deterministic and not predictable. So usually describe probability. So it's something like every time we have, because the value we measure will be not the same for every time. So it is just inside the domain. And like last week, we have introduced, we have a topic both teeth sensors. So this is the sensor that's inside a robot. So it's something like inside a joint or to measure the position or torque of the joint. So this kind of sensor measures the internal states of a robot, something like position, velocity of joints, but also torque or the accelerations. And another one will be the extroceptive sensors. So it is measuring the environment. So usually we will implement this kind of sensor to the end effector of the robot. So it's measure the characteristic a robot interact with the environment. So something like you can have the false pulse sensors, proximity or visions. So we'll start with the proprioceptive sensors. The first one will be the position sensors, because the position sensor is very important because we want to know what our robot's configuration is at any time. So it's like if my arm is a robot, so I only know that because like here, I don't know what the degree of my OO is, then I won't know what is the position of my hand. So like, if I know my shoulder is 0 degree, and here will be 90 degrees, then I can calculate by the forward kinematics, then I'll know my hand's position and rotation. So the position sensor will be very important in the robot. So it provides an electrical signal proportional to the displacement of the mechanical parts with respect to the reference conditions. And we have two kinds. So the first one will be the linear displacement sensors, and the second one will be the angular displacement sensors. And the angular displacement sensors is mostly used in robotics, since all the linear motions we can measure through the rotating motors. So this is the encoder. It's what we use inside the robot to measure positions. And the encoders, so this is the shift of our rotary encoders. So it is measuring the rotations. Can be classified into two categories. So the first one will be the incremental encoder, then the second one will be the absolute encoder. The incremental encoder, so the output of the incremental encoder is the pulse signals, and by counting the pulse, or by time the pulse with user clock signal, then we can increment the distance. So we can count the number of the pulse is sent to us, then we can do a calibration and transfer it into the distance or the angle it has. But this kind of sensor, we always need a home position, or we can call it a reference point, because it's only counting the pulse, and we didn't know where it starts. So we always need to give a starting point. Then like each pulse is like 5 degrees. Then the first pulse will have 5 degrees. Second pulse will increment into 10 degrees, then 15 degrees. So we know what is the position of the joint. And the second one will be the absolute encoder. So an absolute encoder has many pulse tracks on its transducer's disk. When the disk of the absolute encoder rotates, several pulse trends equals to are generated simultaneously. So we'll see the figures afterwards. You'll know this kind of sensors better. So this is the incremental encoder. So you can see this is a disk, so you will rotate with our joint. And here we have a light source, and here we have a receiver. So if the disk rotates, the light will be blocked by the disk and can go through the disk and through the windows. Then we can have the output voltage like this. So this is a one-track incremental encoder. So the optical encoder uses an optic disc. This is a disc. So that have one or more. So here we have only one. So a beam of light is projected to all tracks. So here we only have one beam of light, and the transmitted light is picked up using a blend of photosensors. So here is the photosensors which will pick up the light. And since the light from the source is interrupted by the optic regions of the track, the output signal from the photosensor is a serial of voltage pulse. So it is like this. So you can your sensor will measure this voltage pulse. So like this one will have 3 tracks. So this one will be a reference track, and this one will be that. So these are 2 tracks. So normally we will have 2 tracks or more, or like a little sensor. So the optic rotating disc with 3 tracks. So measure incremental angular displacement by counting the trends of n pulse per turn. So this one will be the track A, and this one will be track B, and it will have a 90 degrees shift. So this is the phase shift of 90 degrees electrical. So it is in the voltage you have 90 degrees. And the third track Z is used as a reference, so you can know your home position is here, and you also know that you have already rotated 1 full cycle. So this is the voltage output. So you can see like for V1 will be the A, and V2 will be the B or B track, and C will be the reference track. So between we have a phase shift for 90 degrees. So you can see it here. So like for this point, here will be dark and here will be light. So you can see it's maybe like, oh, it's here. So the track A is dark and the track B is light. And with me, so it's just dark inside. Between the dark, just light. I think it's good for this voltage, we need to shift 180 degrees for the second track. But it's just present figures for this, that you can see what is light and dark. So, and we also can determine by these 2 tracks to determine our directions. So we'll have a clockwise and a counterclockwise. So if we see here, if this is dark and light, and the next one will be dark and dark, and here will be light and dark. So depends on the sequence. We can determine which the rotation of the joint is clockwise or counterclockwise. So our displacement measurement. So the maximum count possible for an increment encoder is n pulse, and the range of encoder is positive negative theta max, and the angular position is theta corresponding to a count of n pulse is computed as this is theta, and we have n over n. So this is our maximum displacement. And also, our resolution is governed by 2 kinds of resolution. The first one will be the physical resolution, and the second one will be digital. So the physical resolution is the number of windows n in the curved disk. So here we have like 1, 2, 3, 4, 5, 6. We have 6 windows. So if we manufacture these disks, then the resolution, the physical resolution of this disk is already being determined. And another one will be the digital resolutions. It is the digital size, because we need to save all this information in our like memories in the computers or memories where whatever. So we also have the digital resolution. It is governed by the digital size. And for the digital resolutions, so like if we all depends on how many bits we want to use. So we can just see here, like we have one round is 360 degrees, then it depends on how many bytes we want to use. If like 2 bytes, we only have one byte, then we only have 0 and 1. So we only have 2. So we can only, so the resolution is 180 degrees. Because like one round is 360 degrees, then we only have 1 byte. So this 1 byte can only memory like 0 or 1. So we only have 2. So for 360 degrees divided by 2, we only have 180 degrees if we only have 1 byte. And for the physical resolutions, so the number of window n is the coldest, so it is 360 divided by n. And because of we always have like 2 tracks, so we can have another 4 signal available. It's like just now we have the 2 tracks. Here we can have the light, dark, and light, dark. So these are 4 different phases. So for the physical resolution, we can have 360 degrees divided by 4n. And all these 2 are the resolutions that govern our encoder. Then we will find the one which is more strict, then we'll choose that as the resolution for our encoder. So if our digital resolution is more strict, then we can increase our memory, then the bottlenecks will be changed to the physical resolution. So these are 2 examples for the incremental encoders. Like in your mouse, here will be a ball, and the ball roll will rotate this axis, and here will be have a disk, and here is the light transmit. So here is one encoder, and this one will be a second encoder. So like for this mouse can measure the x and y axis, the x and y displacement. And another will be the off-round incremental encoder. So it's 2000 pulse per turn. And this is the absolute encoder. So what is the absolute different from the incremental? So the absolute is like you can each position of the disk have one meaning. So like this one will be light, dark. So when you measure it, you'll know what is the position of the displacement. So an absolute encoder directly generates coded digital words to represent each discrete angular position. And so unlike with an incremental encoder, no pulse count is involved, so we do not need the home positions. And the digital encoder is the digital encoding of absolute positions, and the resolution will be 360 divided by 2. So the n will be the track number, so here we have 4. So the minimum track number for we use for in robotics or in the industrial robots is 12. And a simplified code pattern on the disk of an absolute encoder can use directly like binary code. We'll explain later. So, as a binary code, the data interpretation problem associated with the straight binary code, this one is a binary code disk. So, like here you can see is 0 is 0, 0, 0, 0, and 1, and 2. So you can, this is what will be the first digits, second, third, and fourth. So the problem with the binary code is that if you want to do here, like we need to change all 3 bits, So it's like this one will be 1100 and become 0010. Yeah. So you need to change all the 3 bits. And this will, so if you have some major mistake, then the displacement, the position will be far away from what is the real one. So when the optical disk is rotating fast, the use of binary code may lead to large reading errors. So in this case, we change it to the gray code. So that's each adjacent transition involve only 1 bit switching. So you can see here, it's all dark, and here we only have 1 light and 2 lights, and this one from light to dark. So each number, the adjacent, we only switch 1 code. So this is how you transfer the binary code to the gray code, and also the reverse. So this will be the digit. We can try it after. So this is the binary code. For 0 is all 0, and for 1 will be the same, and 2. So maybe we can try it. So it's like, we can take like 9 is 1, 0, 0, 1, and we can just go down by 1. And it's because the 1 is different from here, so we have 1. I think it's here is different, so it's 1, and here is same, or be 0, and here is different, so it will be 1. So I think it's okay. And so this one will be from binary to gray code, and from gray code back to binary, we'll hit 1, and this 2, 1 is the same, so it's 0, and this 2, the 0 is the same, so also 0. So for the practical use, we use the gray code disk in the robots. So because as just mentioned, the binary code disk will be changing a lot of digits at once. So if you see here, this one will be 1110, and it's for 7. And if it changes to 8, it's suddenly become 0001. So all the 4 digits change. So we, in the practical, we want to avoid this kind of problems. So we don't want to change a lot of digits at once. So because like the auto signal, if it is light, so maybe it's 1, then it's maybe like this is the ideally output. But in reality, our maybe will be something like this. And if the robot rotates very fast, so the changing will be much faster, much rapidly. So we want to like you can see the outside this contract is dark, light, so it changes every number. So if we change to gray code, the changing of it is digits will be taken longer. So we have two numbers as dark and 2 numbers as light. So for practical use, we use a gray code. And so we also have the problem of converting the binary code to the gray code. So here again. So, like for example, if we take the 12 for the binary will be 1, 1, 0, 0, and 1, 1, 0. And if we want to convert into a gray code, so the first one will be 1. And as for the first digit and second digit is the same. So it's 0. And the second digit and the third digit is different. So it's 1. And the fourth one, the 2, 0 are the same. So it's 0. So here we convert into the gray code. So it's 1, 0, 1, 0. And how do we convert back to the binary? Because this is, we only convert into gray code and we want to manufacture the disk. And what we read from the sensors is the gray code. So in our processing, we need to change the gray code back to the binary. So back to binary, 1, we also take 1. And now we compare these two together. So this is 1 and this is 0. So it is different. So here will be 1. And we also compare these two. So it's 1 and 1 is the same. So it's 0. And we compare these two. So 0 and 0 is the same. So it's 0. So we convert it back to the binary. And now this is the velocity sensors. So here we have a magnet. So here we have a magnetic field, and this is the this will be rotated inside here. And by rotating, so in the magnetic field we have a coil. So here we'll be producing voltage. So the voltage will be sum up, and the sum up the voltage amount, then we can know what is the velocity of the robot joint. And this is an example. So it's bidirectional, you can have positive or negative. So the upper voltage is 11 to 24 voltage is at 100,000 RPM. And the weight is around 0.113 gram, and the diameter is 2.9 centimeters. So these are all listed in the spec of these sensors. So if you want to design a robot, then you need to know what's your spec. So you need to know what's the properties you want, so you can refer to the spec and choose the right sensors. And also, this is another one is the accelerometers. So just now that one is measuring the velocity. And this one will be measuring the accelerations. So the measure of linear acceleration is based on the inertial force, so without touching. And the unit is usually the meter per second square, or in gravity. So G is equal to 9.81 meter per second square. So different principles for converting mechanical motions in electrical signals. So the first one is piezoelectric. So it's by converting the mechanical motion into the electrical. So it's usually convert the pressure to the electric. And also the piezoresistive. And also another one will convert sensitive. And usually for our model solution, we use the MEMS sensors. And this kind of the accelerometers, we have different applications such as measuring vibration, or we can also measure the long-range navigations. So the accelerometers we also have in your cell phones or like other type of robots. So this is one kind of the accelerometers. So by accelerating, we have a force pulling the spring or pushing the springs. So the spring, the distance of spring will be different, and the mass will be hitting the pressure on the piezoelectric materials, and the piezoelectric material will generate voltage, and we can measure the voltage. And based on the voltage measured, we can define the accelerations. And this is a MEMS. So, like here we have two. This is the measuring the thing. So here will be a mass is here. So the spring will be like if you have acceleration, then this one will be moved in the moving plate. Then depends on the here by sensing this one, we can know the amount of accelerations it generates. So it's measured. And this kind of sensor is very small and light. You can install it in a lot of places. And these are the example using the accelerometers in robots. So the Bosch DNA is 3 XL accelerometers. So it's integrated in 2 large textile models on the link. And also, this one is the sensor installed here. So by using this kind of sensors, we can measure the acceleration of the robot link. Just now, other sensors will measure the velocity or position of the joint, but the acceleration usually will measure the link, because the joint won't really move, it rotates, so the link have the accelerations. And we come to the exosensitive sensors. So it's basically this kind of sensor is measuring the environment. So this is the pulse sensors. So maybe all of you know it is strain gauge. So this is the indirect information obtained from the measure of deformation of an elastic element subject to the force support to be measured. So you can see here is like we have a strain, then have a deformation, then we can measure the difference, and we have a tension, then we can measure the difference. So this is the compression. The length will be the shorter, and the displacement will be larger, deformation will be larger for the tension. So this kind of basic component is a strain gauge. So uses the variation of resistance R of the metal conductor with its length L of cross section X. So a strain gauge is used to measure strain. So it converts the mechanical displacement into a change of resistance. And this kind of sensor will be called the passive sensors. So this is a very thin device that you can attach on like a lot of different places, but the material needs to be can be deformed. So because it is measure the deformations. So if your robot is rigid body, then you cannot place it attached on your rigid body links. So resistance strain gauge is most widely used device for measuring strain. And based on principle that the electric resistance of a conductor change when it's subjected to mechanical deformations. So when a load is applied, deformation results in both semi and resistant elements. So usually you will have two kind of elements, and depends on if there are different deformations, then you can measure what is the amount of deformation. So this is a very well-known Weston bridge, and it's an electrical circuit used to measure a non-electrical resistance. So here we have the first resistance Rx, so it's a unknown resistor, and these two and 3 is a phase value, and this resistor R4 is a variables, and by adding a voltage to AC, and here the G we can measure the voltage output, and we can determine the Rx is equal to the R2 times R4 over R3. And if we change a little bit, then we can use this one as measuring the output delta R over R. Because a lot of materials, as you know, if we change the length or the size, the resistor value will change. So by this, we can get that the resistor R1, R2, R3, R4 may be a strain gauge, and we'll have a DC as Vs, and we're measuring the point B, and D. So by this equation, we can get the relationship between the Vs and Vg. So if the Vg measure is 0, so all these 4 are the same. So the fraction of these two will be the same. So if we're doing, like we have the same for resistor, and we attach to a deformation materials, then if the Vg appears 0, then we can infer that there will be no deformation of the materials. And we also can add 4 variables to the resistor. And doing the same calculations, then we can get this voltage, this deformation over the resistor, and times the input voltage. So have you all known the Weston bridge already? So if I need to do the calculation, you can let me know. So this is a typical green type load cell. So we'll attach the 2 strain gauge up here, and another 2, 1 is beneath this bin. So if we add a load, produce a moment M onto the bin, then the M is equal to Px. So the X will be the gauge location. So it's here. This is the equation, and this is the X. And also by the Young's module, we can have this one will be Y over sigma I over Y. And for the bin, the inertial will be BH previous over 12. And we combine the equation together, and also we use the workflow, and we can get this one. And we substitute in the initial, and we can get this one. So by just now, by the resistance bridge, then we will know that the deformation R over the resistance is equal to what we want to find. So by this, we can measure the deformation. So through the change of the resistance signal. So we put it into a resistance bridge, then we can find the sensitivity. This is just what we get from the 4-ohm resistance bridge. So this is a real experiment for implementation of the strain gauge. So here you can see is a strain gauge, and here this is a deformation arm. This is a robot link. So, but this link is can kind of soft. It's a flexible element beam, so it will be deformed. And they put 7 strain gauge on here to measure the deformations. So by measuring the deformations, you will know what is the position of the robot. So it's measure the local curvature in dynamic during the motions. So by measuring these 7 deformations, then you can calculate what is the position or what is the configuration of this kind of flexible baby robots. And we also use the force torque sensor inside the joint. So this is another type of strain gauge that's measuring the torque. If we just now we mounted the strain gauge onto a beam or a plate. If you mount it onto a cylindrical surface, then you can measure the torque. So strain gauge mounted to sense the axial deformations of the transmission strip of geometry. So this is how a robot can measure its torque of its joint. So we also can use the force torque sensors at the robot wrist. So it is usually like if we have a robot, this is the robot base, and this is the first link, and the second link, and the third link. And here will be our flange. And usually we'll mount a torque or force sensors here. Then we mount our gripper, the end effector, after our sensors. So all the environmental force acting onto the gripper then can be sensed by this force torque sensor. We'll have example afterwards. So because the strain gauge is measuring one direction's force or moments, so at least one such element in any direction along or around which a force or torque measure is needed. So you need to, when you design a robot or you want to design which sensor you want to use, you need to decided how many axes or how many directions of force or torque you want to measure, then you can implement this kind of sensor onto it. And because our environment is 6 degrees of freedoms, but because the deformation of this kind of sensor is quite little, quite small, so we usually use more than 6 to measure our environment. Like if you want like measure the x-axis deformation, maybe you can use 2 or 3 similar strain gauge to measure it. And you can like do the averaging, or you can do other type of calculation to make sure that your measurement is more correct. And so on each element, a pair of strain gauge is glued as to undergo opposite deformation along the main axis measurements. So as just now the Bristol bridge, so we need a pair of strain gauge to generate the resistant voltage. So these are the examples. Like this is the 4 deformation elements here. And we mounted onto the flange here, and this is the M factor. It is kind of gripper. So if you wanted something, some sensors, top sensor like this, then you can measure the deformation, and through a strain gauge, then you can measure the force and torque of the external force acting on the gripper, or like this one will have gravity on it. Then you will know you have already picked up an object. So this is a 6-dimensional 6-degree freedom force torque sensors. You can mount it onto the flange of your robot. So here, this kind of sensor, you can measure all the 3-direction force and the 3-direction torque. And this is how you do the sensor calibrations. So here is the force and the torque. And this one will be the output of the Western bridge signals. And through this one will be the calibration matrix. So through the calibration matrix, you can get what is the force and the torque you want in the 6-dimensional 6-degree of freedom. And so this is called from the output signal to what is to the thing you want. Here will be called the calibrations. So sometimes we need to do many types of calibration to get the really right calibration matrix. And these are the example that these sensors can do. So here will be the 4 sensors. And like this is the assembling, so it's a fast matching. So this is you group the parts and you want to assemble onto the motor. And this is the polishing tool, and you want to polish. So by touching the tool to the object, the workpiece, the surface, you will have a force and the torque, maybe because it is not on the same axis. So you will generate both torque and force. And if you can measure it, then you know you have already touched on the workpiece. And also by assembly, because this one have a rotation motion, and you want to know whether like you doing a school, you want to know if it's fine or not. So you will have a measuring torque to ensure that it's complete the task. So this is another type of sensors. So this one will be a remote sensor of compliance. You can see here, this is all compliant materials, and here will be your grippers. So this kind of sensors is that when you touch when the outside external force or torque applied onto the any factors, this material will deform like this. So through the deformation of the compliant materials, we can calculate what is the external force or the torque on the any factor or on the objects. Like this gripper is placing this one slot into this slot, and how it sense the object is touching together. So this one you can see here, you have the deformation to measure the torque or force, and by adjusting the sensor, the center, then it can place this inside. So this kind of sensor is the passive compliant to the robot's end factor. And we have the proximity or distance sensors. So this is the infrared. So a light source is emitted a ray beam, which then captured by a receiver. So it is something very similar to like the encoder. So, but this one is using the reflecting. And also, like that, in the encoder, they also can use the reflect, but not a window. And also, we have the ultrasound. So this one will be generated by the piezoelectric transducer. Excited by the external voltage. And for the actual sensor, so the distance is proportional to the time on flight, because when you do ultrasound, the time is because this is the energy loss, so it travels to the objects and hit the object and back. So the flying time will be equal to your proportional to your distance. And these are the example of using the ultrasound sensing. So here is a robot, and we place it in a known room. So the robot don't know what is our floor plan of the room, and it's using the ultrasound sensing and hits all the walls, and it's we're traveling, so and then this can sense all the wall of the place, of the surrounding. So by ultrasound sensing, we can do a navigation. And for the proximity sensors, we also have the laser scanner. So the laser scanner is 2-dimensional scan of the environment with a radial field of infrared sensor beam. So it's also a time of flight sensors because we always want to receive our um, because we want to receive our laser beam. So the flight time of the laser beam will be proportional to the distance. And this is a vision system. So usually will be an array of photosensitive elements. So this kind of photosensitive elements convert the light energy into electrical energy. So like this one will be a CCD, it's a charge couple device. So each pixel surface is made of semiconductor device accumulating free charge when it's hit by the photons. And this one will be a CMOS. I think most of our camera or phones using the CMOS as a chip to catch the light. And this is how they do the calibrations. So usually, this is the pixels that's on the CMOS or the CD, and we will have a calibration to nearmap to have the XY. And do the calibration of the, because once you see inside the sensor, the output of sensor is not equal to what is in a real image. So we need to do a calibrations. So this is also like here will be the camera frame, and here will be a real frames. So also we have another kind of like camera is using the reflector. And for the robots, we have a camera, like we can have it on the hand. This is the eye on hand kind of the robot. So here will be the main reflector, and here is the camera. And we need to do the calibrations to let the robot know what is the system of the camera, and also what is the coordinate system of the main reflector. So this is the calibrations. So usually we'll have two different configurations, and the camera will take a photo on the calibration board, and in two different configurations, or you can say two different position or orientations, then we can generate the calibration of the robots by vision base. So this is a KUKA LWR with eye-in-hand camera and full sensors. And I think that is for today's lecture. So do you have any comment for today's lecture? Or any questions based on the sensors? So usually the most important part will be the encoder, because the encoder is used in every robot, and because we want to know the position of the robot's configurations, and through the position, then we can use the mathematical variations of time to get the velocity or even accelerations. So that is not really needed to implement the velocity or the acceleration sensors, but the position sensor will be the most common one. And because doing the derivation will have, maybe it's better than doing the integrals. And maybe we can have a break and we can come back and we'll discuss about our project's information, our project details. Okay, so you can check your group. So this will be the case study groups, and this will be your topics. So if you see any mistake, please come to here. And this will be your presentation dates. And because we have two groups of 3 people, so the group with 3 people, you need to know because you have an extra person to share your work. So maybe our grading will be different to a group of 2. And here is the projects update progress maintenance list. So for group 1 and group 5, we will only have 5 people remain the same. And for 2, 3, 4, and 6, we will have 6 people to do the project together. So similarly, if you have 6 people to do projects, we will expect you to have more products. So is there any mistake about so we'll go through again. So because some of you didn't came last week, so this course have 2 lectures. One will be Professor Botany, and I'm New Holly. And this is my office and our mail. You can all find it on the Mechanical Engineering Department of Mechanical Engineering website. And Jason is our teaching assistant, so I think all of you have already known him. And we have an exam for this course is as November 5th. And also we have projects. So the project is containing the proposal and the final presentation. And this is the dates. And our grading will have 5% is the attendance, and 9% will be the case study. And we have 4 homework, will be very easy homework. And 6 combining will be 16%. And the exam is 30%, and the project is 40%. And so if you really want to score a very high grade in this course, maybe you need to do very well in your exam, because I think that's the grade that you can really score it. And I think we have already finished for the grouping. And for the project, the 40%, we have 10% for the proposal, and 5% for the progress discussion, and 25% for the final presentation. And this is the presentation structure for the case study. So it's 12 minutes presentation plus 3 minutes for Q&A. And you should have included all this. So it's introduction. So you need to state the definition and the characteristic of your robot field or aspect. And you also need to do the structural analysis. It's like you need to state what is the link or the joint or how it's controlled, and also the sensors and actuators used in those kind of robots. and you can explain some of the applications, the examples, and what is the impact. And also you can do the classifications. Maybe it's within your topics, or is how you classify this one, your topics, your robots, with other types of robots. And also you need to cite your reference. So we expect you not only find your information online or in the website, you also need to refer to some textbook or some papers or conference papers, journal papers. As this is a course for graduate students. And again, this is our schedule. So next week we will have a holiday. It's the Mid-Autumn Festival. And mid of October we will have the proposal. So please submit the report before the proposal ends 11th of October. And another 2 weeks at November 5th, we will have our exam. And we'll have an industrial tour. Our Jason will explain later. And here we have a progress discussion to check whether you are on progress and give some feedbacks. So the last day will be the final presentations. And also the report should be submitted before your presentation. So yeah, you can explain.
And we are planning an industrial tour to Highway on November 26th. And we will depart from Taiwan Tech at 10:30 a.m. and the visit will take place from 1:30 p.m. to 2:30 p.m. And if you do not have classes in this morning and would like to participate, please fill out the form, and I will put the form after the class, and I will put on Moodle and Facebook group. And Highway will need to conduct a data review before the visit can take place. Okay. Thank you.
So this is it's ready for your final report. So you can choose your title by yourself. So this is the design or analysis of robotic systems. But depending on what your robot is, you can define your title. So it will match your project. So for introduction, so this project is meant to engage students in designing modeling and analysis a robotic system to address real-world problems. So you need to specify your problem first. Then with that problem, you need to design your own robots, take solutions. Maybe it is only one robot, or you want to have multiple robots working together. It depends on you. And then this is the opportunity to apply the theoretical knowledge in the class or by your own study to the practical challenge in robotics. And for the aim is you need to identify a problem in the field of robotics, and next you need to design a robotic system that can solve the problems. And you need to do the theoretical backgrounds, such as analysis of robotic systems. So maybe like using some theoretical approaches, like we will teach later in the class. the forward kinematics or the inverse kinematics or the Jacobian and the statics analysis, something like that. And you also need to do some practical simulations. These practical simulations depends on you, what you're familiar with. You can, a mathematical model is also counted as a simulations. So maybe you can just give the matrices, the reference frames by MATLAB or something like that, just verify your calculations. That is fine. And also you need to present the project in clear and well structure. So as this is a graduate class, so we want you to propose your report in the actual academic structure. So as a proposal, you'll have a problem statement. Here you have clearly defined the problem your robotic system and to solve, and you need to do the background and related work research. So it is a literature review. So all the relevant background information on the problem and review the previous research or existing solution to similar problems. So you need to compare what your proposed solution is different or improved from the others. So I think this will be the important one. And I know because some of you are from robotics labs, so maybe you have previous work from your lab, but some of you maybe not. And here you need to really state what are the works from your lab and what are your own. So here you need to describe any your works is like previous to these projects. And you need to state your objectives, so you can outline your specific goals of the projects. And the task, you can break down the objective into the task, and you need to describe some approaches to accomplish the task. And the last one will be the schedule. Maybe you can use the Gantt chart or something like to manage your time schedule. And the last one will be the reference. And here I will give you an example for a proposal, but it's quite long, so you do not need to do this much. But this is an example for a research proposal. So the title will be a robotic exoskeleton for assist as neat gut representations. So you can add your own your own sections to it. So here we start with the summary, and this is the table of contents. And by the introduction, you will explain what is the problems and like this is like the survival rate, so you will state the problems, and you need to say what's your problem you need to solve, and what is the condition of the problems, and how this is important, and so then you need to do the overview. So this is the background research of the relevant topics, and it's compared with so it's given a table, so and it's compared with the others, so you can know what's your different from the existing robots. And this is the previous work. So here we state that this work has already been done. It's not new to this project, but you can base on these works that and then you can doing, and then you can just continue your research. And here will be the most important is your research objective. So you can just state it. And also to achieve your objective, you need what's the task you need to do. And the methodology and the approach is the way how you to complete your objective. So maybe using the knowledge you know now. It is like because you do the background research or the literature reviews, you can reference how they do their projects and what are the methodologies they use or what are the approach they use. You can use the same approach of the experiments. So this is a modeling of the robots and give by some equations, and then for the last one will be the gunshots or the schedule. So by scheduling, you know, so you list the tasks you need to do and you define a schedule. And because this is quite a long report, you don't need to do that long, maybe like half or maybe less than this. And you need to cite your reference in the correct format. And this is the example. And continue with the final report. The final report is continue with your proposal. The introduction is basically the same, but you need to summarize your objective and you need to tell us what you have achieved. And the background and related work is almost the same with your proposal, or maybe you can add some more as because you research and you are more familiar with the topics. And all these are optional. It's not really mandatory. So you can adjust your structure as you want. But basically, in the research papers, the introduction, the background, and related works will appear here. But the marketing research is optional. This is to do the market analysis. Is what is the marketing of your robotic system? Is there similar products in the market, and what the cost of it? If you want to do maybe really like the cost-effective robotic system that can solve the same problem, then it will also be a good idea. And this is the methodology and the robot design. So you need to describe the approach, how you design the robots, and including the components such as the sensors, the actuators, and the controller you use. So you need to provide your design diagram or sketchbook illustrating the structure of your robotic systems, and you need to explain the process of integrating these components into your systems. And also you present your final design. And next will be the mathematical modeling and simulations. So maybe if some of your team members are familiar with CAD, then you can use the CAD software to design to show your robot design. And the kinematic modeling or other modeling is like the control model, like PID control or something like that. If you know, or it is not. So all these are not compulsory. So it depends on what's your knowledge and what you have already done your research. So you need to learn a lot by yourself. So based on your interest. So also you can provide a simulation performed to validate the design. So for maybe the easier is using MATLAB and just simulate it through the mathematical models, just all the metrics come together, then you can have the position and the acceleration and velocity of the any factor. Or you, for the like more advanced, if you know how to perform all this in rows, then you can model it in rows. A really robotic platform to do the simulations. And you need to take your result and discussion and summarize the results obtained from the simulations of the robotic systems. And you use the bigger graphical table to present the data. And discussion the robot performance and evaluate how well this meets your objective. And also you can identify your limitations or your improvements in these robot systems. And also the reference. And for the robot requirements, so try to minimize your typos, spelling, grammatical errors. I know because all of us will make this mistake, it's fine. And ensure you proper label and caption all the figures and cite all literature you use in the reports, because as if you are doing academic, you really need to cite other people's work. You cannot just take it as your own. So this is very important. You need to cite all the literature. So and you need to present your finding logically and clearly, and you use the right reference format. So the proposal is around 10 to 12 pages, and the final report is 15 to 20 pages, and no more than 10 figures. And the page limit doesn't include the title sheet and the contents page and reference or the appendix. So if you have a lot of figures you want to present, you can put it in the appendix so we can see it. Because maybe you did a really great job like doing the CAD or something, and you want to present the figures, and also maybe you can like upload a supplemental file if you do a really like video or something like that. And you then use the Time New Roman 12 and 1.5 line space. So this is about submission. So only one report is needed to submit by each group leader. So if you, I think the first member will be the group leader, right? Yeah. So or you can just discuss yourself. You need a group leader, and the group leader is responsible for submitting a single report for the group. And each group member, you need to, including the leader, you must submit individual's A4 page and describing what's your contribution or what's your learning to the group projects. And for the proposal, the submission date is 11th October. The presentation is 15th October, so it's 4 days before your presentation. And for the final report, so its submission date is 1 week before your presentations. So it's more like the oral exams. You need to submit your report before the presentations, not after. So because I know a lot of reports, and Professor Lin and I will read through all the reports before your presentations. And the presentation will be on the last day, it is the 17th of December. So is there any question about the final report? And all this document will be uploaded to the Facebook group and the Moodle. Because it's like the final report is around like 15 to 20 page, and you have like 5 to 6 people per group, so everyone might share 3 to 4 pages or maybe less. Yeah, so is there any question about it? Or if so these are all recommended structure, but you can, if you have a better structure to present your work, then it's fine to use your own structure. I think that's all for this lecture. Thank you. So if you have any problem, you can come up to me.